Good afternoon, dear student, and welcome to this fifth edition of our numerical method class. So without any further ado, I think we should start. So what are we going to do today? Today we are going to tackle rational functions and particularly Paddy approximation. So that's what we are going to cover today. Or I'm going to introduce the concepts. If you recall what was done previously in terms of polynomial approximation, because don't forget that now we are dealing with approximation theory. And approximation theory is when you have a set of data points and we want to approximate that set of data points, or you want to approximate a function. The function might be known analytically, or it might be known through a set of data points, and you want to find a representation of that set of data points using an algebraic expression. Okay, if you recall what I said with respect to polynomial approximation, I told you that the drawback of polynomial approximation is particularly due to the fact that there are oscillation at the endpoint, which we also call wiggles. At the endpoint, there are wiggles. Oscillation. Using polynomial does not give a good approximation. So one way to remediate or to mitigate that is to use a rational function approximation. That's one way. Okay, with polynomials are easy to manipulate. As you know, polynomials are easy to manipulate. There are many things that you can do with polynomials. But rational functions are ratios of polynomials. So let's start with the definition of what is a rational function. A rational function is denoted here by Rx, which is a function of one variable x being a real number. A rational function of degree n is a function of the form. So a rational function can be written as the ratio of p of x by q of x, where px is a polynomial of a certain degree, let's say m, and qx is another polynomial of an arbitrary degree, say n, right? So m is the degree of the numerator, the polynomial in the numerator p, and n is the degree of the polynomial in the denominator. Now, the degree of this rational function will be the sum of the two polynomials. So if the degree of p is m and the degree of q is n, capital N will be the sum of m and n. So that is roughly the definition. Okay, I will not go into all this, but I will go straight, right? So you can write a rational function in this form, given by equation 1.21 or 1.21. Okay, so that is the general form of a rational function. When we know the degree of the numerator and that of the denominator, please note that this is m. You can correct it on your slide. It is m, not n. You can see here, we say p and q are two polynomials of degree m and n respectively. So, okay, p is n and q is m. So q is this one. So this one is m in the denominator. Okay, so let me modify that right away, so that anyone who will be watching this will know that here This is M. Be able. M. Okay. Okay, now if you want to approximate using this expression, how many unknowns or coefficient do we need to determine here? Here we have n plus 1, and here in the denominator we have m plus 1. M. So this also is m. 2, 2. 2. M. M. Okay, so we have to define or to determine, we need to determine a total of n plus m here, n plus 1 in the numerator, and in the denominator m plus 1, which in total will give us capital M plus 2. Capital N being n plus n, because we have this plus that, which is capital, plus 2. That's the number of coefficients if you use this formula. So we can reduce this number by 1. And how do we proceed by, how can we do that? By assuming that this is non-zero. Why can we assume that this is non-zero? We can always make that assumption. Why? Because if this is 0, at 0 it can give you 0. You see. So if Q is 0, when X will take the value 0, this will not be defined at 0. You see, that's why it's a problem. So so we can assume that it's non-zero. And if you assume that it's non-zero, it means that this Q0 is non-zero. Therefore, we can factor by Q0 in the numerator and the denominator and cancel out. In that way, if you cancel out, you are reducing the number of unknown in the denominator by 1. Therefore, instead of having n plus 2 unknowns, you will be reduced to n plus 1, which is not negligible. It's not negligible. Okay, now if you do that and you cancel out, you see that the coefficient here will be 1. Because it is non-zero, you factor, you cancel out, therefore the coefficient here will be 1. So that's why we say we can assume that Q0 is always equal to 1. So we can assume it, and I've just explained why. Because you can factor by Q0 if it's non-zero, and then cancel out. Now the coefficient that we have here will be Q1 divided by Q0, which is non-zero. That you give it a new name, you give it a new name. So at the end, you have a total of n plus 1 parameters by just renaming. Okay, if you rename, you can still rename it Q1, Q2, even though it's a certain Q1 prime and P0 prime and whatsoever. Doesn't matter, you can recall the new parameter using the previous names. It doesn't matter. We do that regularly in mathematics. Shouldn't be a problem. Okay, so this being said, you see that we reduce the number to this. I already explained here. Okay, so that is, we have prepared a stage. Now let us dive straight into the Padé approximation method. Okay, so what is the purpose here? We want to approximate a function or a set of data points. They are equivalent, right? But in our case, in this class, for now, you'll be given the function you want to approximate using the Padé approximation. That function will be given to you. Its analytical expression will be given. The only thing you have to do will be to write is Taylor expansion or the Maclaurin expansion series of that function f. So we want to approximate the function f using a rational function. Right. So we know the expression of the rational function Rx, which is given by this, or you can use this, And we know that this is the same as this expression. So now the purpose is to determine or to design an algorithm that will allow us to compute all these coefficients, P0 up to Pn and Q1 up to Qm, assuming Q0 is always 1. We reduce the number of parameters. So that is the purpose. Now, how do we proceed by so doing? First of all, we compute the ratio, the difference, f of x minus rx. So it gives us this one. Then we cross multiply to obtain the same denominator. Now, if you do that, and we replace q and p by their respective values given by here in equation 1.21, right? We can write this as a general polynomial, that is using the summation. So if we substitute the expression of q and p, this is what we get. So you agree with me that it would be much easier to write the Taylor expansion of f of x for us to, because if you don't expand this will not be useful to you. It will not really be useful. So the idea here is to expand f of x in the neighborhood of 0, because remember that Maclaurin series is Taylor expansion series when x0 is equal to 0. So we are in the neighborhood of 0. And in the neighborhood of 0, we don't want the denominator to be 0. So that's why we made this restriction. Sorry, the HOD is calling. Sorry, Katiban, I'm in the class.
Oh, okay.
Okay. So, okay, so as I was saying here, that it is easier to perform the Taylor the Maclaurin expansions of this function f of x, which will always be the case. So if we can write it this, the Taylor expansion about 0 or the Maclaurin expansion can be written like this. Now we will identify the coefficient of f by a sub I. So this will be the coefficient. But the good thing here is that we will not use the entire series expansion. We will not use the entire series expansion. Why? Because our rational function here, you can see that its degree is finite. And you fix the degree, and by fixing the degree, this will allow us to truncate this expansion. We will see it with an example. We will see that you don't actually need to know all the terms. You just need to know a few of them because they will be useful in the algorithm that we are going to describe very soon. Good. Now, if we substitute that expansion here in the numerator, we are going to design our algorithm in such a way that we will only compute this n plus 1 coefficient, this n plus 1 parameter. So that is the purpose now. We are going to design our algorithm in such a way that we will not require these terms in the Maclaurin expansion series or series expansion of f of x. Now, how do we go about it? Okay. Now, if you look at the substitution, right? After substituting, this is our numerator. This is what we have. Great. Now, the next thing is to differentiate this difference a certain number of times. We are going to differentiate it a certain number of times, and the following observation will allow us to make a decision about how we are going to proceed in our algorithm. Okay, now, if we compute the derivative, that is the derivative of this function, let's say k times, where k will vary from 0 to n. So If we differentiate this difference, if we differentiate this difference, and we impose that at 0, this will give us 0. That's something we impose. It's not that it will be the case, but by imposing, this will lead us to consequences or to some restriction on this coefficient. I repeat again. This condition is something that we impose. It doesn't mean that it will be true if we differentiate that a certain number of that and at 0. No, we are imposing in such a way that this will give us a system to determine our coefficient. So this is something that we impose. We impose it. We impose this condition. And now, by imposing it, what is the consequence of this imposition? The consequence is the following. The consequence is what we call the multiplicity of the root of a given function. So I will explain that. Surely, I think I did that in the first semester. I think I defined the multiplicity during the first semester. What were we dealing with? What were we dealing with when I defined the multiplicity? I recall. Does anybody recall when I defined the multiplicity? I think it was with you during the first semester. Multiplicity, I think I defined this during the first semester in numerical method 1. Anyway, let me recall that. Let me recall that. What is the multiplicity of? But I know that I did it. I did it. I will recall. I will recall. Let me use. Okay. Multiplicity. Let me share a new screen. Okay, multiplicity. So I would notice the multiplicity. or the roots of a function. Okay, now let's assume that x, let's call it alpha. So assume alpha is a root of the function f. We assume is a scalar function of one variable, right? So if it is a root, it means that f of alpha is equal to 0. This is what it means. Now the multiplicity of alpha, I will call it m. M is the multiplicity m, or a real number, a natural integer, a natural integer or positive integer, so an integer, an integer m is called the multiplicity, or the, right? It's called the multiplicity of alpha if, obviously it's the smallest, it's the smallest number, if we can find a polynomial, a function g such that if there exists a function g obviously defined also from R to R such that f of x can be written as x minus alpha x minus alpha to the n times g of x with g of alpha non-zero. This is the definition of multiplicity. So if we can write this, if f can be written this way, where g of alpha is non-zero, where alpha is the root or a root of x, then we say that m is the multiplicity, and m is the smallest, right? Integer m such that this is true. Is the smallest. It is the smallest. Why is it the smallest? Because if I square this, for instance, if I just square this, square and square also this, you see that this will become 2m and square here. If I substitute f of x, it will still give us 0. You see, but that m will not be the minimum. Sorry, what am I saying? That m, you can see that this will still be true if I take a multiple of m. If I square this, for instance, to a certain power, and you substitute, it will still give you 0. When you substitute f of x equal to alpha, it will still give you 0. But at that time, the exponent that you get here will not be the minimum. You see, it will be larger than m. So which means that when you get this a certain m here, that m might not be the multiplicity. It might be a multiple of the multiplicity. To make sure that it is a multiplicity, it has to be the smallest such that this is true. Okay, so, but that's not that important for now. Just let's understand that this is the definition. Okay, now, there's something I want to say. If I differentiate this, let's differentiate this and see if we will still be getting f of the the derivative of f at alpha. We are going to check if it will still give us a 0, right? Because remember that in the previous slide we differentiated a certain number of times, but we're still having 0. So that's what we are going to check now. Now, if I differentiate and assume that this is the minimum. Okay, now if I differentiate this a certain number of times, for that, let us take an example. I will use an example to exemplify what I want to illustrate. So now I take an example. Let's say, for instance, f of x equal to let's say 2x squared minus 4x plus 1. Oh no, let's say plus 2 even. Right. So this, I know that 1. If I put 1 here, 1 there, it gives me 0. Right? So I can say f of, for alpha, in fact, alpha 1, f of 1 or f of alpha, which is f of 1, is 0. But I selected this because I selected it in such a way that the multiplicity is 2. That's my choice. So in this case, m is equal to 2. M is equal to 2. Why? Okay. I can write this as 2 into 1 minus that square. You see? Or I can say that this is x minus 1 squared times 2. So what is this 2 for me? This is my gx. Now you can see that g of 1 is 2, which is non-zero. So at alpha, this is not 0. So you see that it satisfies this definition. You see, it satisfies the definition. So m is 2, this is our multiplicity. Now, if I differentiate this, f prime of x, what is it? F prime of x will be 4x minus 4, right? And that is still 4x minus 1. You see, 4x minus 1. And I have f prime of alpha, which is 1, is also 0. So meaning that alpha is also a root of the first derivative. But now if I differentiate 2 times, 1, 2, then it gives me 4. from here, f double prime of alpha, alpha being 1, is not 0. So now what is this? This 2, the second derivative, is equal to the multiplicity. Okay, so in other words, I can write that f, the k derivative of f at alpha will be 0 for any k less than m. If k is greater than or equal to n, the derivative, I mean the root of the derivative applied to alpha will not give 0. And this is an example. You can see. Once I reach a multiplicity, I can't get 0 anymore. Okay, so bear this in mind because that's what we will use in our Fourier approximation. So recall that if I differentiate, okay, or I can, or this is still true for, this also means that the k derivative of alpha is equal to 0 for k, taking the values 0, 1, up to m minus 1. Because once I reach m, it's no longer 0. So this is a consequence. And you need to remember this. Very important. So if the multiplicity of a root is m, then all the derivative till m minus 1 at the root will give you 0. So that's what I want you to remember from this. Good. Now let us go back. Let us go back to this, the note. Right? So bear this in mind. So if I want to know the multiplicity from differentiation, when I differentiate, I will know that if I differentiate up to this one, I get 0 at the root, and the next one gives me non-zero, it means that the root or the multiplicity of this function f will be m. It will be m. Right? If I stop at m minus 1, it means that the multiplicity is m. Okay, now back to the previous slide. So if I go back to the previous slide, what do we see? Okay, now if this one, you can see this difference, I will call it, let me call this, obviously this is f, but if we replace the name of the previous function that we just, the one that I framed or I boxed in the previous slide, if I call that function, let me call this difference, let me call this difference h, right? So h is the difference between f and r. What is this expression? This is the same as h to the k at 0, because our alpha here is 0, is equal to 0 for k starting from 2 this value, remember that this value should be what? M minus 1. So if I add 1 to this, give me the multiplicity of this function. All right. And that's exactly what we have here. This is the multiplicity of the root. Root of multiplicity n plus 1, right? So that's why I went back to multiplicity and I explained to you what this means. I hope it is clear now for everybody. So this imposition leads to the fact that the multiplicity of this difference, or the difference f minus r, this function f minus r, its multiplicity at the root x equal to 0 is n plus 1. That is what it means. So that's what we are imposing. We are imposing that fact to obtain the algorithm that will allow us to determine all these coefficients. So that's something we impose. We impose it. Okay, now what is the consequence of that? It is so simple. The consequence of this fact, of the fact that this is a multiplicity, the multiplicity will be n plus 1. The consequence of that is the following. Consequently, so that's the consequence here. The consequence will be that this coefficient will be chosen so that the numerator on the right hand side, this one, this numerator, this one, the numerator has no term of degree less than or equal to n, meaning that in the numerator, what will appear will be the degree from n plus 1 upward. That is what will appear in this expansion, in this expression. So all the terms from k equal to 0 up to n in the numerator will be set to 0, because if only this degree appears, it means that the rest are zeros, right? These are the only terms that will appear. These are the degree that will appear. Degree, that is, if you group, if you write this, because this is an expansion, you group, you multiply this, expand everything, then it will start from x n plus 1, of course, a certain coefficient here, that coefficient that we just, oh, sorry. So I'll have a certain coefficient here. Of course, it's this coefficient, but I don't want to write that. X n plus 1 plus another coefficient n plus 2 up to infinity. Why up to infinity? Because here you have an infinite sum here, this one. Because if you expand this, this will stop. This contribution of q will stop at a certain level. Similar for this one, but this one, because it goes up to infinity, the a sub something will continue, right? They will continue, they will continue, they continue. But all the lower terms, that is all the coefficient of that expansion from 0 to n will be set equal to 0. Meaning that if we set the coefficient of this expansion where k runs from 0 to n, it will give us a system of capital N plus 1 equation in capital N plus 1 unknowns. So it will be a linear system that we will be solving, and it will give us exactly this number of parameters. Because remember that the total here is capital N plus 1 parameters. So if we have a system in these parameters and the number of equations is equal to the number of known, we have a unique solution, right? So that's exactly what we are doing here. So now let us see what we will obtain if we let all the coefficients of this expansion, where k runs from 0 to capital N, to be 0. What is the system that we will obtain? So that is the next step we are going to perform now. Okay, now, okay, I will erase this. Okay, good. So we are going to expand this. We are going to expand all this term, and we will take all the coefficient of xk, where k runs from 0 to capital N, and those are the ones we will set to be 0, right? Because of the multiplicity, remember that all those terms should be set to 0. So now let us expand this. Let us expand the numerator. So this is the numerator. This is the Maclaurin expansion, if you recall. In the Maclaurin, the coefficients here are a's. Now for q, this one, we have q, and the remaining terms are in p. So this is exactly what we have, right? So this numerator is given by this. So now we expand this. We are going to expand this and look at a generic coefficient that we denote by xk. We will look at a generic coefficient that we denote by xk. And that xk is given by this. The coefficient of xk in this expansion is given by this, right? Okay, let me show to you that this will be the coefficient, because I don't want to skip this stage, because if I skip it, you might not understand. You will just be memorizing, but I want you to understand what is going on here. I want you to understand. So I'm going to expand this, but for me to do that, I will use something that is easy. I will use algebra, simple algebra, for you to understand how we will end up getting this term. Okay, so what I would do, I would go to the next slide and I will rewrite this expression. And I will expand it in front of you, before your naked eyes, right? I will expand it before your naked eyes so that you will see and not say that, oh, you know, something that we don't understand. I will do that for you to see before your naked eyes. You don't need to put anything, spectacles to see like me, but you'll see it anyway. Good. Now let us let me open. Okay, so if you recall, in the numerator of f of x minus rx is, okay, this one, of course. Okay, let me do this. We know that here in the numerator we have qx here, and here we have our, okay, let me write this summation. I running from 0 to infinity, that's what we have here. We have this one, and this is multiplied by q. And q, okay, for q we have the q's here. Let me put j here. and then minus the p's. Okay, now what should I put here? I can put L, doesn't matter. L, X, L. So the numerator will be this one. So I can write it properly here. A0, A1X, A2X squared, and it goes to infinity because this is an infinite sum. But this one is finite. Remember that for Q0 is 1. Then Q1X up to QMXM. Okay, minus, and then we set to 0. So I can write that one. So this will be P0 plus P1X up to PNXN. And that is equal, we let that to 0, but that's not what is important for us for now. Okay, for now, what we want to do, we want to expand this entire expression and look at the coefficient of a certain xk, which I call here a. No. The coefficient will not be a, because if I say it is something, it's something. Because if I say a, because it will be a combination of a, q, and p, right? Combination. So I will call that, okay, maybe c. Yeah? Okay, let me call that c. So this is what we are looking for from this expansion, because this will be a series, right? You can see that this is a series. This is an infinite sum. We can group all together, and then it will be something of this form. You go to infinity. So this one will be equal to this. Right? This one. Okay, now already the coefficient of xk for this term is pk. We can see it because this one is already there, but I need to expand this product. Right. Now, in order for me to expand this, I will show you with a simple case. If I have two polynomials, right? If I have two polynomials that are multiplied, right? If I multiply, let's say this summation, AK, XI, if I multiply two like this, BJ, XJ. If I multiply these two, the result will also be something of this form. Something like this, where this CK will be equal to the sum, like this, of the factor X. Of course, I will have a factor like this. I call this CK. Now I need to use a, okay, I can decide that this is I. So this will run from 0 to this K, right? It will run from 0 to the K in such a way that the sum of these two indices will be equal to K, right? The sum of these two indices. If I call this I and call this J, I plus J should be equal. Okay, so I'm summing on I. Okay. I'm summing on I. So I can take this to be I, for instance, and this, because if I want to sum like this, if I fix this to be I and this to be J, you can see that from this formula, what will be J? J will be K minus I. So I take this and put there, K minus I. Okay, so if I sum on I from 0 to K, and this is I, and this is J, where the sum of I plus J is K, I can write everything in terms of I. So this would be my formula. That's how you obtain the product of two polynomial or two series. This is how you get the coefficient of the product. So if I use the same thing and apply it to this one, I will just readapt, right? So these are my A, and you see that now the B's will be this case, right? The B's will be the case. So for our particular case, the coefficient of xk, which is ck, will be equal to this, but I will replace B here by Q. So in our case, I will just replace B sub something or B whatsoever will be Q K minus I. So therefore, the coefficient of will be, I can copy this, whatever I call it, CK or whatsoever, it will be written as the sum I running from 0 to K, AI Q K minus I. So that is for this product, this one, this factor. Now, if I want to, okay, I will not just, okay, this is for this CK, right? This CK. But for this original expression, this one, in this one, I need to subtract PK. PK, here. I will need to subtract PK. Because remember that I still have X something here. So if I take XK here, the coefficient of XK here, what is it? It is negative PK, XK. So I will add it. I will add it to this one to obtain the final. So that will be minus PK. So that is the coefficient of xk in this expression, including these two factors plus or minus the contribution of the p's. So that's what we have here. So this is the final. Okay, so that's the final expression. Okay, this is what we'll get. So we can go back to our slide to see the system that we obtain at the end of the day, because that's what you will be using each time you solve a problem related to the Pareto approximation. That's what you get. And you see, this is exactly what we found. So it will be this one. Right. Okay, now in this expression, we assume that we extended all the p's, because remember that we have a finite term here, finite here, but this one is infinite, right? So we will assume that all the terms that exceed m and n are zeros. So all the terms in p that exceed n, that is p n plus 1 up to p capital N is 0. And here for q, from m plus 1 to capital N, here is also 0. Because when we write this, we'll assume that our k will run from what? From 0 to capital N. But don't forget that this m and this n will be less. So in our system, we will take this into account, that sum of the term here will be 0. And that's the linear system we'll be solving. So this is the linear system. You set this to 0, you take this to the right-hand side, it gives you this linear system. That's the linear system you solve when dealing with Padilla approximation. Now, this is an example. Remember, I told you that you don't need to get all the terms in this expansion. Because remember, this is an infinite sum. But you don't need to know all the terms. You don't need to know all the a sub something, a sub I. You don't need to know all of them. You need to know all the n, capital N plus 1 terms. That's all. You need to know them. Because in the system here, k will run up to capital N. And that's the same thing you will need to have here. Okay, now we are told to find the 5th degree Padilla approximation of f of x equal to exponential x. Now, don't forget that this 5th degree is our capital N. So capital N is equal to 5. And this 5 is m plus n, right? It's m plus n. Now, you'll be given these two values. But you can see now that in this approximation, when you write your Maclaurin, like here, when you expand, you don't need to exceed 5 because this is the 5th degree. So you can, in your expansion, stop to x equal to 5, but you put the dash to say that it's an expansion. But you will need to know the coefficient A0, A1, A2, A3, A4, up to A5. Why? Because in this system, I need to know A sub I, where I runs from 0 to n, and capital N here is 5. So that's why in your Maclaurin expansion, you don't need to know all the coefficients. No, you only know to know the number of coefficients corresponding to the degree of your Q, of your Rx. That's what you will need to know. Okay, now, if we can just write this right away, you don't need to do all this expansion. It's not necessary. All these expansions are not necessary once you have this formula. Because if you try to expand this, for some of you, if you don't bear this in mind, the final system that you will be obtaining will be wrong. It will be the wrong system. Okay, we'll stop here for today. Because of time constraints already, we have exceeded by 1 minute. So we'll meet again tomorrow morning. Thank you for your kind attention. God bless you and see you next time. Bye-bye.